Welcome to this explainer. Today, we're diving into something that sounds like sci-fi, but is very, very real: the global supercomputing race. We're living in a time where the scale of human engineering is just almost beyond comprehension. We're going to trace the bleeding edge of computational power, looking specifically at the fierce, high-stakes rivalry between the US and China. But here's the wild part. We'll also see how these exact same competing nations are basically forced to link up to solve the universe's biggest physics mysteries. It's a crazy dynamic.
All right, let's kick things off with a genuinely massive number that just dropped on the June 2026 TOP 500 list: 2.198 exaflops. Yeah, it's a number so huge it kind of breaks your brain a little bit, but this isn't theoretical math. This is the actual, verified speed of a single supercomputer operating on Earth right this second. It's the new benchmark, and it is a big deal.
So what does this actually mean? It means we are officially deep into the exascale era. That's a milestone where machines can crunch at least 1 quintillion calculations every single second. To put that into perspective for a second, a quintillion is a 1 followed by 18 zeros. If you sat there and did 1 calculation per second by hand, it would literally take you over 31 billion years to do what an exascale machine pulls off in 1 second. It's an absolute game changer for modeling climate change, simulating reality, and unlocking quantum physics.
So here's the game plan for today. First, we'll map out the global exascale era. 2, we'll look at how line shine takes the crown. 3, we'll check out the American heavyweights. Number 4 is distributed computing at CERN. And finally, we'll wrap up with collaborating on nuclear fusion.
All right, let's jump right into Section 1, the global exascale era, looking at the June 2026 Top 500 data.
Okay, looking at the numbers, for the very first time, humanity actually has 5 distinct exascale systems running. You can see Germany's Jupiter booster system holding its own at number 5, which is Europe's first real leap into exascale, hitting that 1,000 petaflop mark perfectly. But man, just look at those top 4. What we're witnessing here is an incredibly fierce, high-stakes tug-of-war for absolute supremacy, and it is exclusively between China and the United States. They absolutely dominate the peak of this list.
So moving on to Section 2, line shine takes the crown, and Shenzhen's new number 1 system. Zooming in on that top spot, a brand new titan has entered the chat. Installed over at the National Supercomputing Center in Shenzhen, Line Shi just ended a really long run of US dominance. I mean, by hitting 2.198 exaflops, it isn't just winning, it's sitting more than 20% ahead of the second-place system. That's a huge margin. It's actually a monumental shift because the last time a China-based system led the top 500 was the Sunway Taihu Lite, way back in 2017. To pull this off, Line Shi is running on nearly 13.8 million cores. It's just a massive, custom-engineered beast using their proprietary Kylin OS and Linkkey interconnects. But don't count the US out yet. Let's look at Section 3, the American heavyweights and the US exascale systems. So yeah, while China holds the absolute crown right now, the United States has this incredibly dominant density right at the top. They occupy ranks 2, 3, and 4, and every single one of those systems pushes past that 1 exaflop barrier. You've got El Capitan at the Lawrence Livermore National Lab doing 1.809 exaflops, then Frontier at Oak Ridge with 1.353, and Aurora at the Argonne Leadership Computing Facility rounding it out with 1.012. The big takeaway here? It's the sheer concentrated volume of computing infrastructure housed within the U.S. Department of Energy's National Lab system. It's a serious heavyweight lineup.
And what's super fascinating is that if we put the top 2 systems side by side, it highlights 2 completely different engineering philosophies. Over on the left, China's line shine is basically going with pure brute force. It's distributed over 13.7 million cores using 304 core processors on their custom Lincoln platform. So it's a massive CPU-only design. Now on the right, America's El Capitan takes a totally different hybrid approach. It pairs AMD EPYC processors with AMD Instinct accelerators across 11.3 million cores. This hybrid setup gives the US a real edge in mixed precision tasks, which is absolutely crucial for AI and machine learning stuff. On the flip side, Line Shine's CPU-heavy design is highly specialized for traditional floating point calculations, which is exactly what you want for intense physics or weather simulations.
Now, having all that hardware in a single room is just one way to look at computing power. Let's head to Section 4, distributed computing at CERN and the LHC grid.
So quick question for you. What is the most powerful supercomputer ever built? If you've been following along, you'd probably shout out Line Shi, right? But if we look outside of single dedicated facilities and kind of rethink what a supercomputer can actually be, the answer shifts from these giant mainframes to an incredible global network.
Enter the grid. When scientists were trying to process the insane amount of particle collision data coming out of the Large Hadron Collider in Europe, they realized pretty quickly that literally no single machine on Earth could handle the load. So they just built their own network. They connected regular desktop computers and servers across 170 different locations in 36 countries. It seamlessly shares processing power and data storage across borders. By linking all these individual machines to act as a single unified brain, a lot of folks consider the LHC grid to actually be the most powerful distributed supercomputer ever built. It really goes to show that the ultimate power might not be locked in a basement somewhere, but distributed globally.
And that exact spirit of international teamwork brings us to Section 5, Collaborating on Nuclear Fusion, looking specifically at the ITER project. Here is where things get really interesting. While nations like the US and China are competing fiercely on the top 500 list to build the fastest individual machines, they are simultaneously pooling those massive computational resources for ITER. If you don't know, ITER's goal is to harness practical fusion energy, literally creating the power of a star right here on Earth inside a massive magnetic device called a tokamak. But doing that means solving some of the hardest technological challenges imaginable, like figuring out how to manage extreme heat exhaust and testing neutron-resistant materials. You can't do that alone. It requires the combined, integrated resources of the world's leading scientific powers.
It's such a fascinating duality when you think about the US-China relationship in science. On one hand, you have this intense race for exascale supremacy, but on the other, both countries are deeply, heavily committed to making ITER a reality. I mean, they are literally manufacturing vital, massive components for the exact same shared reactor. The United States is over here supplying these incredibly complex transmission lines for the electron-cyclotron heating system, while China is building massive magnet feeders to bring cryogenic cooling to the superconducting magnets. They are literally building a machine together.
And it's not just about bolting hardware together. It's about shared software and simulation power too. Using state-of-the-art simulation software, researchers from the US, France, and China successfully collaborated to prove that a specific type of plasma instability, known as the fishbone instability, can actually be reduced by self-generating strong flows within the plasma itself. That might sound like a bunch of jargon, but it is a massive breakthrough. You have competing nations using their absolute best computing prowess, not to beat each other, but to directly advance humanity's shared quest for clean, limitless energy.
But just to leave you with something wild to ponder. Despite all of this unimaginable exascale power we've talked about today, that massive LHC grid is currently only able to process about 1% of the data it actually receives from particle collisions. 1%. So as we push the absolute limits of traditional exascale machines to understand quantum mechanics, you really have to wonder, will the physics we discover through these global collaborations eventually birth quantum computers that redefine this entire global race? Could exaflops become obsolete overnight? Well, that's a question for another day. Thanks for joining me on this Explainer. Until next time, keep questioning the limits of what's possible.